Eh, buenas tardes a todos. Me da mucho gusto el día de hoy
So, good
estar
afternoon,
aquí con
everyone.
ustedes en
I
esta
am
otra
very pleased
conferencia
to
de la
be
serie de
here with
conferencias del
you
Comité
in one
de
more
Flujo de Agua y de
conference
Calor en
of
Medios
the
Porosos de la
series
Sociedad
of
Mexicana de Ingeniería
flow of
Geotécnica.
water in
Pues
porous
me da mucho gusto el día de hoy también
soils from
recibir
the Mexican
al doctor
Society of
Alessandro Rotaloria.
Geotechnical
Nos
Engineering.
acompaña el
I
presidente
kindly
de la
welcome
Sociedad
Dr.
Mexicana de
Alessandro
Ingeniería Geotécnica,
Rotaloria.
Miguel
We
Ángel
also
Mánico
have
Narco.
the chairman
El
of
doctor
the Mexican Society
Mánica,
of
perdón. No sé
Geotechnical
si quieres
uh,
comentar algunas
Engineering.
palabras.
Dr.
Bueno, en
Manica,
primer lugar,
you
quiero
have
darle
the floor.
la bienvenida a todos los
Well,
presentes. Muchas
just
gracias por la asistencia.
welcome
A la
the
doctora Norma Patricia
participants.
por organizar este
Thank you
seminario y
very
toda la serie
much,
que ha estado muy, muy
Dr. Norma
interesante. Muchísimas
Patricia,
gracias
for
por el gran
organizing
aporte, doctora. Y
these,
desde luego al doctor
and
Alessandro,
of
Mr.
course,
Alessandro, thank you
Dr.
very much for being
Alessandro
here. It's really
Rotaloria.
an honor and a pleasure. And I'm sure this will be a very exciting and very good presentation. Thank you very much. De mi parte sería todo, doctora.
Gracias, Miguel. Thank you very much, Professor Alessandro Rotaloria, for being here with us and accepting deliver this wonderful conference for our Mexican community. We are very, very lucky. I met you maybe some years ago. Thank you very much for being here. So, I will speak in Spanish. La conferencia del día de hoy se titula Cambio climático
The
subterráneo,
title of the
amenaza y
conference
recurso para
today
las áreas
is
urbanas del mundo. Voy
Underground
a leer la
Climate
semblanza
Change,
del doctor
Threat and
Alessandro
Resources
Rotaloria.
for Urban Areas
Eh,
in the World.
el doctor
I will
Rotaloria es
read
profesor
Dr.
adjunto
Rotaloria CB.
Duisberger en la
He
Universidad
is
Northwestern, donde dirige el Laboratorio de
Professor
Oportunidades y
Louis
Innovaciones
Berger at the
Subterráneas. En
Northwestern
inglés se
University, where
denomina
he leads the
Surface Opportunities
Laboratory
and
of
Innovation
Underground
Laboratorio
Opportunities
y
and
tiene las siglas hoy
Innovations, or Subsurface Opportunities and
en
Innovation
inglés. Su
Laboratory.
investigación se enmarca
His
en la interacción de
research
mecánica,
is
energía y
framed in the
electroquímica
interaction
con
between
énfasis en el
mechanics,
subsuelo,
energy, and
a través de un
electrochemistry,
enfoque que combina métodos
emphasizing in the
teóricos
subsoil.
computacionales
He
y
combines
experimentales. Su
theoretical,
trabajo busca
computational,
avanzar
and
en la comprensión
experimental
fundamental
methods.
de
His
cómo la
work is
transferencia de
looking
energía
for
afecta las
an
relaciones entre
essential
las propiedades y la estructura de
understanding
los materiales
such on
geológicos y
how the
granulares.
energy transfer
Estos conocimientos
affects
tienen como
relationships
objetivo
between
impulsar la
properties
innovación en
and
infraestructura
material
civil y la
structures.
construcción, además de
His
promover
knowledge
la
are
preservación de
intended
entornos naturales
to
urbanos.
drive the
El doctor
innovation
Rotaloria es coautor del
and in
libro
civil
Análisis y
infrastructure.
diseño de
Dr.
infraestructuras
Rotalori
energéticas y ha
is a
contribuido
co-author of
con
the
dos
book
capítulos de
Analysis and
libros, dos
Design
patentes
of
y más de
Energy
100
Geostructures. He
publicaciones
has
en
contributed
revistas
with two
científicas y
chapters of
memorias de
books,
congresos. Su
patents, and
trabajo
more than
ha sido
100
difundido
publications. His
recientemente en
work
medios
has been
internacionales como The
recently
New York
spread
Times,
out
The Washington
in
Post,
international
Financial
media
Times,
such as the New
Scientific
York
American,
Times, the Washington
CNN,
Post,
BBC,
Financial
Naciones
Times,
Unidas, Forbes
Scientific
y New Republic.
American, CNN,
Además, su
BBC,
investigación ha sido
United
exhibida
Nations,
en la
Forbes,
Bienal de
and Bloomberg.
Arquitectura de
In
Venecia
addition,
y
his
presentada en
research has
formato
been
TED Talk.
shown in
Ha sido
the
reconocido
architecture
como
bienal in
Board Innovator
Venice
in
and
the
presented in the form of a
35
TED Talk.
de
He
del
has been
lista de top
acknowledged
100
as a world
del
innovator
Instituto
under
de Tecnología de
35 by
Massachusetts
MIT
y ha
Technology
recibido
Review.
numerosos
And
premios
he
entre los
has
que destacan
received
el
a lot
NSF
of
Career Award,
awards,
the Northwestern
among
University
which we
Curriculum
have
Innovation
NSF
Award,
Career
the
Award, the Northwestern
ASCE
University
Emmy
Curriculum
Leonardo da Vinci
Innovation
Award.
Award,
Y bueno,
ACME
por
Leonardo da
supuesto,
Vinci
él
Award, and
impartió la
of
conferencia
course,
Bright Spark,
he
que todos
delivered the
reconocen para la Sociedad
conference Bright
Mexicana de
Spark
Ingeniería Geotécnica,
that
perdón, para la Sociedad
everyone
Internacional
knows
de
in
Ingeniería Geotécnica, entre muchos otros
SMIG and
premios. Me da
among
mucho
many
gusto el
other.
día de hoy
I
dar
am
la
very
más cordial
pleased
bienvenida
today
al
to
doctor
kindly
Alessandro
welcome
Rotaloria.
Dr.
Thank you,
Alessandro
Alessandro.
Rota Loria.
Muchas
Alessandro,
gracias
thank
para
you
la
very much.
introducción.
Thank you very
So buenas
much for
tardes.
your kind
Good
introduction. Good
afternoon,
afternoon.
everybody. It's a real pleasure to be here. So I would like to thank you, Patricia and Miguel, for the kind invitation. I'm very happy to be in a position to have this interaction with the Mexican community of geotechnical engineering and geomechanics. So as it has been introduced, now I'm gonna share my screen.
Alessandro, before
Yes.
starting, I just want to mention, because there are some comments in the chat, there is live translation available for those that want to listen in Spanish. Para aquellos que quieran escuchar en español, hay traducción simultánea. Ahí en las herramientas, en la parte inferior del Zoom, deberían de encontrar un símbolo que es como un mundito. Ahí pueden seleccionar el idioma de su preferencia, ya sea inglés o español, ¿no? Para que lo tengan ahí presente.
Una disculpa, también olvidé decir que es bien importante, en la barra inferior, igualmente
I
a
also
la
forgot to
izquierda
mention
del
that
círculo que acaba de
on
mencionar el
your
doctor
toolbar
hay
to the left,
un recuadro
there
de
is
preguntas y respuestas.
a box
Dice
that says
Q&A.
Q&A. If you have
Ahí,
any
por favor,
questions,
les
please
solicitamos
type
que
them
hagan
in
preguntas,
the
que hagan
Q&A
sus preguntas, las
box.
pueden hacer en español. Y hay una
You can
traducción
ask
simultánea, como ya lo
questions in
mencionó el doctor
Spanish,
Juanito,
and
que
we have
se
simultaneous
expresarán al
interpretation.
doctor Rotalori.
And we
Gracias.
will, of course, translate them into
Adelante,
English to Dr.
Gracias.
Rota.
So, as it has been introduced, today I will talk about a phenomenon that is often called underground climate change, or more precisely and technically speaking, subsurface urban heat islands, which is a phenomenon that has been studied in a number of other fields, in environmental science, transportation engineering and science, but to date received very limited attention in the field of civil engineering and especially geotechnical engineering. And essentially, I will show you how this phenomenon, that as a matter of fact characterizes all cities worldwide, it's present underneath all cities worldwide, not only represents a threat, but also a very substantial resource for the clean energy transition of cities. Now, this work is the result of the efforts of a number of collaborators with whom I've had the opportunity to interact over the past 10 years. And they are included here in this slide. And of course, I'm very thankful for all of their contribution. And again, to Dr. Lopez Acosta and Monica for providing the opportunity to actually share the results of this work with you and the Mexican community. So the presentation will be divided in 4 main parts. I will start talking about energy-related challenges in urban areas and really introduce the phenomenon of underground climate change. Then I'll talk about one of the possible solutions for underground climate change, which are energy geostructures. I will then focus on the analysis and design of these novel types of geotechnical structures and conclude with a number of application examples. So starting with energy-related challenges in urban areas, the message is the following. So you all know that we also, as a result of rising global population, we need more and more energy. What you may not know, though, is that most of the energy that we actually consume in buildings is for space heating and cooling and hot water production. In fact, depending on the country, from 40 to 70 and even 80% of the energy that we use in buildings is actually used for heating, cooling, and hot water. In the context of Chicago, so where I live, as a matter of fact, this percentage is 60%, so even more than 60%. And the current practice is problematic because essentially all of this heat typically comes from non-renewable energy sources, and that have as a direct consequence the generation of CO2 gas that then leads to global warming and climate change. Now, of course, we can produce heat with electricity, and so this is why we are trying to electrify our world. But as a matter of fact, if we could use directly heat, it would be a much more efficient way to meet these thermal energy needs. And so the first remark that I would like to convey is we need substantial amount of energy, and specifically thermal energy, typically above the ground. Now, if you look at what we have underground, I'm used to show these 2 postures, which I think exemplify very well the concept of geothermal energy, and the concept that essentially beyond a few meters of depth in the ground, the temperature remains relatively constant throughout the year. So these are two posters that were designed by Frederick Herrick for the London Underground, for the Tube, the metro system in London. And back in the 1900s, they were showing how during the hottest days of the summer, it is cooler below. And during the coldest days in winter, it is warmer below. And really the message of these two posters is that the temperature in the ground remains relatively stable throughout the year. So it is warmer than the mean temperature during winter and cooler during summer. And this is a reality that you can find everywhere in the world, in principle. So if you dig a hole underground, you're going to find a relatively stable temperature with depth that is going to be approximately equal to the mean annual surface air temperature. For instance, here in Chicago, like the annual surface air temperature is of approximately 11 degrees Celsius. And so if you dig a hole outside of Chicago, at least, you're going to find 11 degrees Celsius. Before, where I was living before, and I obtained my PhD, so in Switzerland, in Lausanne, for example, the annual surface air temperature is 13 degrees Celsius. And if you dig a hole underground, you're going to find more or less 13 degrees Celsius, and so on and so forth. In Mexico City, very likely you're going to find a higher temperature because the annual surface air temperature, the average, is going to be higher, and so on and so forth. So the concept is that despite the actual value of temperature will change depending on where you are, what does not change is that this temperature is relatively constant throughout the year. And so this is really the operational principle behind all geothermal technologies. Now, what I just told you, it's a reality, it's a fact, it's true everywhere, but except nowadays, if we consider urban areas. Because in fact, when we are in urban areas, nowadays we find so-called temperature anomalies. And so the idea is that as a result of anthropogenic activity, and specifically as a result of the operation of underground infrastructure, the breaking of trains, the presence of urban commuters, and the presence of heat sources, what is happening is that the ground beneath cities is warming up. And so this is the so-called phenomenon of subsurface urban heat islands. So subsurface urban heat islands represent an underground climate change because they lead to a change in the environmental, in the thermal conditions underground. And so I guess many of you have heard multiple times talking about extreme urban heat and surface heat islands or meteorological urban heat islands. But as a matter of fact, there is the flip side of the coin also developing underground. So essentially what is happening is that the urban subsurface is warming up with temperature, increasing temperatures of up to 2.5 degrees Celsius per decade, which put into perspective is actually higher than the current rate of global warming in the atmosphere. Till recent years, temperature anomalies of up to 30 degrees Celsius were measured in the underground. And I can tell you that as a matter of fact, right now with my colleagues, we're working on a number of cities. We're working to monitor this underground climate change in a number of cities. And we have measured up to 70 and even 80 degrees Celsius in the ground beneath our feet, in the ground beneath cities. And this again is due to the operation of like tunnels, parking garages, and for example, district heating lines. So all of these underground infrastructure and utilities continuously reject heat underground, and essentially this heat is building up. Okay, if you have traveled to London or to New York or in all major cities, Mexico City, but like in all major cities that have, for example, underground transportation network and so on and so forth, you might have already experienced how hot it can be. Now, underground climate change is a recognized environmental issue because basically in a number of cities, it's leading to, it's affecting the environment by essentially influencing seed germination, plant growth, and affecting biogeochemical cycles. It is also a public health issue because, again, for urban commuters, not only they can experience thermal discomfort, but they can also experience heat-induced diseases such as asthma and heat-induced stroke. And there are recorded cases every year about these this influence of extreme heat underground for urban commuters. It is also a transportation infrastructure issue because it can be so hot underground that oftentimes the rails of trains can be at the onset of buckling. And so basically trains need to slow down or even stop, with costs associated with delays. And also heat can lead to an accelerated aging of infrastructure. But so despite these renowned consequences of this extreme underground urban heat, before my group and I started to work in this field, we didn't really know what could have been the effects of underground climate change on civil infrastructure, for example, on geotechnical structures. Now, the idea is that, as you might expect, so geomaterials, so soils, rocks, and concrete, so in general cases, when they are heated up, they expand. And this is kind of what we would expect rationally. However, if in soils specifically, and fine-grained soils under normally consolidated conditions, for example, or under particular conditions, they do not expand upon heating, but they contract. And this phenomenon, which has been widely studied in the literature, is oftentimes called thermal collapse. So the idea is that when a fine-grained soil is heated up, instead of expanding, it actually shrinks. It volumetrically shrinks. And these contractions are actually irreversible in nature. So there are plastic phenomena associated with them. And so really, the question at the time was, what's the influence of urban ground warming? What's the influence of underground climate change on the performance of civil infrastructure? So how large are these deformations, and can they represent a problem? So we started to work in this field, and we essentially studied this problem with a focus on Chicago. And it turns out that underground climate change can represent a problem on a case-by-case basis for the operational performance of civil structures and infrastructures, including, of course, geotechnical structures. And so while we shouldn't be concerned about the safety and the stability of the structure, so we shouldn't be concerned about achieving ultimate limit states, there can be situations where we may actually achieve serviceability limit states, and so states which are problematic for the function and long-term durability of structures and infrastructures. Now, let me be more specific about all of this. So essentially, what we did as a part of this work was to use Chicago and specifically the Loop District, which is the downtown area of Chicago, as a living laboratory. So due to the proximity of Northwestern to Chicago, essentially the idea was, let's use the Loop District as a living lab, and let's study, first of all, the presence of an underground climate change beneath Chicago, and second of all, whether this underground climate change might have led to substantial deformations. The subsurface of Chicago is a very, it's an emblematic example of how much we use the underground nowadays. So of course, it hosts like a sewage system, a district energy network. There are underground pathways. There are more than 400 basements, underground parking garages. Actually, the Loop hosts the largest underground parking garage in the US, with more than like 8,000 parking spaces. There is a subway system. There even is a theater underground. And then there are a myriad of tunnels that were built over the years. And so really the idea is that in all of these environments, there constantly is the generation of heat, which sooner or later will permeate, will diffuse into the underground. Another characteristic of Chicago is that it rests on a shallower layer of sand and backfill material, but then essentially it rests on layers of fine-grained soils, and specifically normally consolidated clays as well, and also over-consolidated clays. And so really, we are dealing with a stratigraphy where we have materials that will both expand but also contract upon heating. So what we did as a part of this study was to deploy more than 100 temperature sensors downtown to really measure, on the one hand, the temperature that characterizes these underground environments, such as like building basements, parking garages, and so on and so forth. And on the other hand, we wanted to also quantify what's the temperature really in the ground itself. And so here you have an example of the sensors that we deployed underground. and we really deployed them in myriad environments with the ability to gather more than 20,000 temperature data per day. So we literally like transform the city of Chicago into a living laboratory. And here you can see, for example, what these readings tell us. So essentially, since 2019, we have been able to collect temperature data for downtown Chicago every day, every hour of the day, and really to monitor what is happening in the city. And here, I guess you have an interesting piece of information, like an experimental piece of information. So in this graph, you can see basically what is the average surface temperature in Chicago throughout the year in red. Here you can see the value of the temperature that we found in the ground in a park located downtown Chicago, so far from heat sources. Whereas here you can see instead the temperature that we found in the heart of the loop, so really next to buildings downtown, like in the heart of the district. And so as you can see, there basically is a temperature difference, like there is a temperature anomaly, at least on these points, of about 10 degrees Celsius. So what this data allows us to assess is that Chicago, like all cities worldwide, is experiencing an underground climate change. So the ground beneath Chicago is warming up and has warmed up. And so really the question was, what's the influence of these temperature variations on ground deformation? So we know that all materials deform when subjected to temperature variations. And so the question was, what's the influence of these temperature variations on ground deformations and the interconnected performance of civil structures and infrastructures? So what we did to explore this project with all these underground environments. And what we did was essentially to simulate the process of heat rejection that has happened in the loop over the past 75 years, more or less, with then the aim to predict what's likely to happen in the next 25 years. So what we did was to simulate a time frame of 100 years, starting from approximately 1950 till 2050. And here you can see a comparison between essentially numerical simulation results that are these like curves, and with these dots and markers, you can see the experimental data. And so you can see how without any fitting, so we didn't apply any fitting at all in this model, we were able to reproduce the process of heat diffusion in the underground. So we were able to essentially simulate how much heat has diffused over time in the underground beneath the loop, and to basically validate the capability of our model to reproduce this problem. The simulations that we ran were thermohydromechanical, so not only they allowed us to simulate the heat diffusion process, but also the impacts of this heat diffusion process on groundwater flow and the hydraulics of the problem, and clearly also on the deformation of the system. So we were able to assess the so-called thermally induced deformations of the ground, so the deformations that this heating process has caused. Before getting there, here, so in this slide, you can see basically maps at different depths of the temperature distribution in the ground beneath Chicago, beneath the Chicago Loop district. And the message is that the darker the color is, the higher is the temperature variation compared to the initial undisturbed ground temperature. Whereas the lighter the color is, the closer is the ground to undisturbed conditions. And so basically what you can see is that in the regions where there is the higher building density, of course, you have more purple, which means, again, you have more temperature anomalies in the ground. And clearly, like the deeper you go and the farther you are from the buildings, the less significant are going to be the temperature anomalies, the temperature variations that are leading to this underground climate change. Now, before I told you that some soil layers in Chicago are normally consolidated and others are over-consolidated. And so you can see how, like, what has happened and is happening and will continue to happen over time is that Some layers of ground are contracting, like essentially they are shrinking over time. Whereas other layers, typically the hard clay, the over-concentrated clay, is expanding. So you have there is a complex interaction between different soil layers that essentially is causing the ground beneath Chicago to move, if you want. And when considering the effect, when considering the deformation of these normally consolidated deposits, which are shrinking, you may essentially think about the fact that this underground climate change is leading to a new form or different form of land subsidence, because that's at the end what it is, what all of this is. Here you have a graph that essentially shows you what's the magnitude of the displacements, of the vertical displacement. So we know, in geotechnical engineering, oftentimes a key parameter, a key metric is vertical displacement, and we know that excessive vertical displacements can lead to unwanted effects, such as well, of course, differential and average displacements matter in general, and these can lead to excessive deflections, angular distortion, tilting, and all of these phenomena eventually can lead to cracking, which in the long term can bring durability issues. And so, as you can see, compared basically to the settlements caused by the mechanical loads, so the dead loads acting on the buildings, the displacements caused by thermal loads vary, of course, depending on the heating rate, and they can be significant. So we're talking about displacements of tens of millimeters. We're talking about displacement of centimeters that, of course, have developed over a long time frame. We're talking about 100 years, but still they have developed over time. And so essentially, based on the magnitude of this displacement, we can say, so we have postulated that some of the operational issues that have been documented in Chicago over the past decades might have been exacerbated by this underground climate change. So of course, it's difficult to speculate, and actually we don't want to speculate, but at least based on the order of magnitude, we can say that in our opinion, these displacements are large enough to potentially represent a problem for, again, the function and the long-term durability of structures, because they are of several, tens of millimeters, they are of several centimeters. And so they're something that is non-negligible. And it's something that is caused by these underground climate change and these rising urban ground warming. Now, so before I go to the next section of the presentation, I would like to stress how, again, the phenomenon of underground climate change characterizes all cities worldwide. As soon as we build a construction, there is going to be an interface with the ground. And no matter how well insulated that building is, there will be some heat that will leak into the ground. There will be some heat that will diffuse in the ground. So really, underground climate change is an endemic feature of our presence on Earth and of really anthropogenic activity and our construction on Earth. All cities, this study was focused on Chicago, but right now we're working on the city of Boston. We have worked on the city of Lausanne in Switzerland and other cities worldwide, and essentially all of them experience this underground climate change. And clearly, a city like Mexico City definitely has a subsurface urban heat island due to the myriad of essentially buildings that constitute the city. Now, how can we mitigate these phenomena? Well, essentially, there are two ways. Before I'll go into one, before I'll describe one, I would like to say that, of course, the best and most efficient way to mitigate underground climate change is to improve energy efficiency by thermal insulating underground building enclosure. And so basically limiting the amount of heat that is released at the source. So by thermal insulating underground building enclosures, we can essentially limit how much heat is released in the underground. And so we can limit really the intensity of this underground climate change. The second approach, and I will partly talk about this, so the second approach instead consists of utilizing geothermal technologies to get back the heat that would be wasted otherwise. So the idea is that geothermal technologies can be used to absorb this waste heat and bring it back to buildings and use it. So essentially turning waste heat into a resource. And so today I'll talk about a specific example of shallow geothermal technologies, which are called energy geostructures. They are a technology that has developed a lot over the past 20 years. And now it's a technology that's been increasingly implemented worldwide, and essentially consists of integrating traditional geotechnical structures with traditional shallow geothermal heat exchangers such as boreholes. The idea is essentially to put plastic pipes with water circulating into them in the simplest case into the reinforcing cage that constitutes pile foundations, retaining walls, slabs, tunnels, whatever you can think of. And so essentially the idea is that you can transform structures into energy sources. You can transform structures into heat exchangers. And so here, and the idea, before I go ahead, sorry, and the idea is that essentially with these technologies, you can absorb not only the geothermal heat that is present underground, but also the waste heat that we are releasing and bring it up where it's needed in buildings. And so meet our space heating and hot water production needs on top of cooling needs. So here you have an example of what energy piles can look like. So it's nothing special to some extent. I mean, these are board piles equipped with these plastic tubes, with these black plastic tubes where water will circulate into. And so these piles are essentially transformed into so-called energy piles. These are energy barrettes. So again, large pile foundations used typically to support tall buildings, which are transformed into energy barrettes. Here you have slabs. So clearly you can deploy these pipes within the base slabs of buildings. You can deploy the pipes also within retaining walls, like in diaphragm walls, for example. So you can thermally activate these structures. And these you have examples of segmental linings, which essentially are transformed into energy segmental linings or energy tunnels in general. Now, the limitation, if you want, of traditional energy geostructures, though, is that they are only applicable to new construction. So classically, we needed to build these structures in order to be able to put the pipes in. So to overcome these limitations, together with my collaborators, we have invented essentially the world's first geothermal panel called EnerDrip, which is a panel made of aluminum alloy that can be installed on the inside of any underground space, typically on walls. It is also provided with customized and customizable panels for advertisement and so on and so forth. But really, the idea is that it can transform existing structures into energy geostructures. And like all other types of energy geostructures, it allows us to absorb heat from the ground and also from the air that circulates in underground environments, and that typically embeds waste heat. The idea is that then this system is connected to a heat pump, and then this heat pump will provide the heating and or cooling to buildings or infrastructures. So really, the idea is to transform all kinds of underground constructions into energy sources to contribute to the decarbonization of buildings and to contribute to the clean energy transition of cities, irrespective of whether underground constructions already exist or not. So the key take-home message is that energy geostructures can be deployed both in existing buildings and in new buildings. Here we have like an idea of what the actual panel looks like. So it's been deployed in a parking garage. So you can see all the panels connected with each other. And this is the same installation, just with these like finishing panels on top that protect the panels from external perturbations, let's say. Now, for what can we use energy geostructures? Well, as I told you, you can use them for space heating and cooling, hot water production. You can also use them to de-ice structures, so to avoid the formation of ice and snow, which can be very useful, for example, for the decks of airports, like airport runways, or even for like sidewalks and roads. Importantly, they can also be utilized for thermal energy storage. So the idea is that you can use the ground as a thermal battery. At the same time, when implemented in tunnels, for example, they allow us to reduce ventilation requirements in tunnels. And as I anticipated before, they can also be used for thermal networks. So the idea is that if you're dealing with a tunnel and you turn it into an energy tunnel, you can transform that asset into an energy producer. So essentially, the tunnel can start harnessing energy not only for its own use, but also sell it to consumers, to sell it to real estates or energy contractors, or in any case, people who have interest in purchasing energy because they need it or they want to sell it again. So the idea is that these technologies, so the operational principle of energy geostructures is the same like all traditional geothermal technology. So you have a primary circuit underground that then is connected to one or more heat pumps, which is a device that converts mechanical energy into heat. And then you have a secondary circuit in the building that essentially delivers the heat. So really here, nothing is different. The only difference is that instead of drilling a hole next to a building, and so instead of installing a geothermal borehole, we integrate those pipes, those heat exchanger pipes, into geotechnical structures and underground constructions, which means that there are gains in, there are cost savings involved, because essentially we would have already built those structures in any case. So we don't drill the ground only for the sake of the heat exchange, but essentially we use structures that will be built in any case, and simply we provide an additional role, a new multifunctional role. And as I told you before, we transform these structures into energy sources, and sources of geothermal heat, which is available 24/7, irrespective of the weather, and everywhere on Earth. So irrespective of whether you are in Mexico, anywhere in the United States, in Italy, in France, in South Korea, or like South Africa, you are gonna have that heat available. The typical return on investment of these technologies ranges from 4 to 15 years, with an average of 8. So these are typically projects that attract a lot of interest because they make economic sense and they have a number of advantages. Now, from an engineering perspective, though, what are challenges that need to be addressed for these novel types of structures? Well, there are energy challenges because, of course, a key question is how much heat can these structures provide? What's the energy that we can harness from the ground? Then, due to the fact that we're going to have temperature variations, a second question is, or a second challenge consists of a structural challenge, because the question is, what's going to be the deformation of the structure? Is it going to be, do we need to limit it? To which extent is it going to be important? And then, of course, since they're going to induce temperature variations into the ground, we will have interest in controlling them to avoid unwanted effects, okay? And so today, I will focus mostly on structure and geotechnical challenges given the audience, although I would say nowadays, there is knowledge about all of these three aspects, and we know very well how to analyze and design energy geostructures. From a high-level perspective, though, really here the scientific question at first and the engineering question later, and now practical question was, compared to traditional underground constructions, how do energy geostructures behave due to the influence of temperature variations? How do they deform, for example? And so in the third portion of this talk, I will actually show you the results of some activities, some models that we have developed over the years with my collaborators, which are included in this book, which I had the opportunity to write with Professor Lalui from EPFL, the Swiss Federal Institute of Technology in Lausanne. And that really summarizes all the tools and techniques that we can use to address the analysis and design of these technologies. From a high-level perspective, there are essentially three approaches as we have them to analyze and design more traditional geotechnical systems. We have charts, so we have developed charts over the years to analyze, typically for feasibility assessments and schematic designs. We have developed analytical models to address the analysis and design of these technologies with hand calculations. And then, of course, there are the more rigorous but more time-consuming numerical approaches that can be used. So with respect to the charts, the idea is that besides charts that allow us to understand how much power can be harnessed from the ground, the charts that we have developed basically allow us to understand, depending on the site conditions and the geometry of the structures that we're dealing with, what are going to be the thermal induced displacements, stresses and moments and so on and so forth. So these are really graphical approaches through which we can very quickly and easily take values that then we can use for feasibility assessments to understand how to cope with these temperature variations. With respect to analytical models, essentially what we have done in this field has been to extend very classical analytical models available for the analysis of traditional geotechnical structures, such as the interaction factor method originally proposed and formulated by Paulos and co-workers and Randolph and co-worker, to non-isothermal conditions. So what we have done has been to extend it to non-isothermal conditions to be able to account for temperature variations. We have done the same thing with equivalent peer method. Also, the Winkler analysis of beams resting on a soil. And lately, we have also extended the classical cavity expansion theory to non-isothermal conditions, really to be able to account for temperature variations for the analysis and design of tunnels. And so in the following, I will basically fly over the main features of these tools just to show you that basically they exist and they can provide very accurate values of displacements and forces and moments that act on these structures, and they are caused by temperature variations. So here you have like an overview of what the interaction factor method is. The idea is that this approach aims to address the displacement of pile groups based on the superposition principle. And so by essentially assessing what's the degree of interaction between all the piles in a group through the definition of an interaction factor for mechanical loads and thermal loads. And so here really the main novelty was to determine the interaction factor caused by thermal loads. For this, we developed like two analytical models that represented extensions of a model originally formulated by Randolph and Roth and the classical Midland solution. But so the idea of these models is that essentially we calculate the extent and the magnitude of the interactions between all the piles. And based on the knowledge of these interactions, we can then apply the elastic superposition principle to calculate what's going to be the deformation of the energy pile group subjected to any kind of temperature variations. In this slide, you can see a comparison between experimental data and analytical data, and you can see how good the results can be. Like, as long as you consider representative material properties, you can really capture quite well what happens in reality. Here you have an overview of what the extension of the classical Winkler solution looks like. And the idea is that it's very similar. The idea is to use the elastic principle of superposition to analyze essentially what's the influence of a given combination of loads on one beam, and then apply the superposition principle to study the interaction between multiple beams that can lead to a plane geostructure, such as, for example, a cut and cover tunnel or a retaining wall or whatsoever. And here again, like in this slide, you see a comparison between the results of the analytical model and numerical simulations, and you can see how close the results are, meaning that essentially this analytical approach can capture well the effects of temperature variations. And I'd like to stress that for the sake of this demonstration, in this case, we consider just the unitary value of loads, just for simplicity, and so the effects are very minor, but the model, as a matter of fact, can be used to assess the effects of any magnitude of mechanical loads, as long as they remain within like the elastic domain. And here, last but not least, you have an example of how we extended the classical cavity expansion theory. So the idea is that we included in the mathematical formulation of this very traditional approach the effect of temperature variations. And so nowadays we can actually use it to estimate, for example, what are the thermal induced radial stresses or Hoop stresses within tunnels, within cavities, if you want. And again, there is like a close comparison between numerical results and analytical results. Now, as I told you before, of course, the most rigorous approach, although more time-consuming approach, consists of numerical models. And nowadays, there are a number of formulations, again, thermohydromechanical formulations that allow us to capture many aspects involved in the heat diffusion process in the subsurface, its impact on groundwater flow, and the impacts also on the deformation. And so these are typically the approaches that are utilized for the detailed design of energy structures. To give an example of what are the things that can be done, and I will shortly arrive to the conclusion, I'd like to share with you the results of some projects on which I have had the opportunity to work on through a company that I co-founded called GeoEgg that really specializes in the design and implementation of energy geostructures. And as an example, I will take this one of this building located in Poland, which is an office tower, for which basically the base barrettes of the foundation in green were transformed into energy barrettes. The base slab in orange was transformed into an energy slab, and the side walls were turned into energy walls. Here you can see how these numerical models were used. So essentially, we built a 3D model for the detailed design to really assess the response of these complex structures. And here, apologies, and here you have examples of results that really tell us essentially what is the magnitude of the temperature variations and what are the effects on the stresses within the structures. These analyses, as a matter of fact, allow us to really study over time what happens in these systems and to then develop checks at serviceability limit states to ensure that everything will be fine over a given service lifetime and operational lifetime. And here you have another example of a tower that has been recently built in Switzerland, the Tilia Tower. That is the largest, so the tallest mass timber building that is currently available in Europe, funded on energy geostructures. So here you can see the plan views of the project, and you can see how the walls and slab were thermally activated. Again, in this slide, we built these 3D numerical models to assess what are the effects of these temperature variations and how much energy we can harness from the ground. And here you can see the system realized. So this is an aerial photo of the project with all the pipes, and this is the engineering drawings of essentially of the location of the pipes. So really from theory we passed to practice, and we implemented this project in a building that will be very soon put in service and start its operation. So here we can see the construction site. All of these are plastic pipes that then go, in this case, into the base slab and then also in the retaining walls. And so really the idea is that this building will be self-sufficient from a thermal energy perspective, thanks to this energy geostructure system and a complementary system of geothermal boreholes that have been built next to the building. So to conclude, I guess the message that I want to convey is that the ground beneath all cities worldwide is warming up, and this is due to subsurface urban heat islands that essentially consist of an underground climate change. Now, the good news is that, again, by improving energy efficiency in buildings, so by thermal insulating buildings, we can limit at the source this heat, this rejection of waste heat in the ground. At the same time, an alternative approach is to deploy geothermal technologies, such as energy geostructures, as a means to essentially absorb heat that would be wasted otherwise, and to repurpose it for our own needs in buildings. So I guess, as the title of my talk suggested from the start, underground climate change, on the one hand, represents a silent hazard, if you want. It represents a threat. But on the other hand, it represents a very big opportunity, because it provides one additional reason for improving energy efficiency in buildings and also deploying geothermal technologies and energy geostructures in particular, which at the time I'm speaking are proven technologies which are affordable, reliable, and characterized by an excellent performance in the long term. With this, I would like to thank again Dr. Lopez Acosta and Dr. Manica for the invitation to deliver this talk, and all of you for listening, and I'm very happy to answer any questions.
Thank you, Professor Rotaloria. Thank you very much for this interesting conference. So, no veo preguntas. ¿Alguien en el público tiene alguna pregunta? Recuerden que pueden hacerlas incluso en español. El
Do
doctor
you
Alessandro
have any
Rotalori.
questions? Please remember that you can ask your questions in English or in Spanish, and we have simultaneous interpretation available.
Gracias, Ana. Bueno, comentaba yo, y lo que quiero decir es, el doctor
Okay,
Alessandro Rotaloria es
Dr.
italiano,
Alessandro Rotaloria
entonces
is
él entiende
Italian.
un poco español o mucho
He
español.
understands Spanish,
Ujú. Entonces también pueden con confianza hacer preguntas.
so you can ask your questions in Spanish too, and he understands Spanish.
Ok, bueno, voy a preguntar. Este tema, Alessandro, en México es nuevo. Como tú sabes, desde hace varios años, aproximadamente en 2017, pues una servidora ha procurado impulsar este tema en nuestro país. Lo que he encontrado aquí es que los diseños, hemos hecho algunos diseños de personas interesadas en esta tecnología. No obstante, hemos identificado que en nuestro país las cargas térmicas para hacer estos diseños son no balanceadas, lo cual efectivamente viene a contribuir a mediano o largo plazo al calentamiento o al sobreenfriamiento del suelo. Ujú. ¿Tú tienes alguna recomendación que hacer en México, en nuestro país, para esto? ¿Pudieras comentar algo?
Sí,
In
but
English.
so, so thank you for the question. So, well, one first comment I would like to make is that so I've been involved over the years in the development of these tools to analyze and design energy structures and really to assess the effects of temperature variations on structural performance and geotechnical performance. And I would say that these are really checks that should be done. And let's say the thermal activations of these structures will basically almost never represented a problem. I can tell you that so far it has never represented a problem because the temperature variations typically remain limited, but they can represent a problem in specific conditions. And so this is why these aspects need to be verified. For example, if we deal with a pile foundation resting on a very rock stratum, on a very stiff rock stratum, in that condition, the thermal induced stresses can be very high. We can talk about several megapascals. In many situations, we might not have that, but in some, we may actually have that. And so that's why these things should be verified. On the other side, if you take, again, a pile foundation in a very soft soil deposit, we've talked about thermal collapse and we have talked about these effects, which again can be very, very significant. So I would say the good news is that nowadays we have available these tools to analyze and design energy geostructures. And all these verifications that we need to do are more checks than anything else for which we should be concerned. And again, with respect to, so this is the first portion of the answer. The second portion of the answer is also related to the significance of underground climate change. So this warming that characterizes those cities has been going on for decades, and we didn't even realize it, as a matter of fact. So is underground climate change generally a problem? No. But again, on a case-by-case basis, it may represent a problem. Again, now I'm working in a number of cities, and we are measuring ground temperatures of up to like even more than 70 degrees Celsius, because there are, for example, district heating lines that operate at 200 degrees Celsius. So clearly, if you have 200 degrees Celsius underground, you can lead to desiccation cracks. You can lead to a number of phenomena that can be problematic. So really, the message that I would like to convey is that, first of all, these things, these phenomena, and all the things we have talked about are certainly interesting from a scientific perspective, but also from an engineering perspective, they provide new challenges and also new opportunities that we should consider. And with respect to the phenomenon that you said, Norma, about geothermal technologies warming up or cooling down the subsurface, that's certainly something that needs to be controlled. And so, as a matter of fact, these technologies use the ground as a heat exchanger. So essentially, when we use them to cool down buildings, we are warming up the ground, like we're injecting heat into the ground. And when we are using them to warm up buildings, we are extracting heat from the ground to bring it, in order to bring it to buildings. So essentially, we are cooling down the ground. So a key aspect that is involved is really to maintain in the long term the temperature field of the subsurface in a stable condition. So, but again, these are aspects that are certainly true. But the good news is that nowadays we have the tools to control them and to simulate them. So again, energy geostructures are now a technology that is proven. It is proven. It has been proven that they work well. They have a high performance. It has been proven that they are cost effective. I guess there really is the need of a willingness to implement them and to be open-minded and to be ready to actually address the few things that we need to do in order to make these things happen, if it makes sense. But we have all the tools to do that. We have the knowledge to do that. Of course, there are still like some gaps and things that need to be explored, but it's not rocket science anymore. These are things that can happen and are happening, if it makes sense.
Gracias, Alessandro. Hay varias preguntas ya, voy a leerlas. La primera de ellas es de José Luis González. ¿Qué riesgos existen en las estructuras o en las personas por el uso de dispositivos de captación y transmisión de calor?
Yeah, so, well, in general, in order to, thank you for the question. But so in general, in order to really assess what are the thermal properties of the subsurface, there are a number of field tests that can be performed. And these are so-called thermal response tests or even thermal performance tests. But essentially, these are tests that allow us to assess what is the temperature in the subsurface and what are the thermal properties of the subsurface. And again, depending on the countries worldwide, these are things that are available on the market. And then when talking about really subsurface heat islands, the idea is that the heat sources that can produce these temperature anomalies can be very diverse. They can be the cars that travel in underground parking garages. They can be the trains that break in tunnels. They can be people walking. We people release 60 watts over time, lighting systems, and so on and so forth. And so all of that heat can also diffuse underground and cause these temperature anomalies. I hope I answered the question. Yeah.
Thank you. En su experiencia, doctor Alessandro, las ciudades están creciendo a nivel mundial. ¿Qué tan costoso es implementar estos sistemas? ¿Y qué problemas tienen que enfrentar los gobiernos al tratar de implementarlos?
Yeah, thank you for your question. So I guess, again, to me, well, the number one thing that is needed is the awareness about the existence of these technologies. So to be honest, again, we have been working in different countries nowadays, and it's depending on the country, it is not yet common practice. So the first thing typically is that building owners need to be aware of the existence of these technologies. Oftentimes when building owners, real estate companies, and even energy companies, when they think about geothermal, oftentimes they think about geothermal boreholes. And I think that the key argument that we as a society and a collective of people should bring is that typically for a given kilowatt of thermal power provided, energy geostructures are more cost effective. They are more economical because we don't have the costs associated with drilling. And so this is typically an argument that needs to be put in front of like building owners, because maybe if they are considering to implement geothermal boreholes, for us, there is opportunity to propose variants and actually say, no, well, you can still install geothermal boreholes, but it can be a good idea to actually create a variant and transform a pile foundation that would be built in any case into an energy pile foundation, because there are economic gains. And again, the return on investment can typically range from 6 to 8 years. So we're not talking about 20 years. These are things that can pay off relatively quickly. So yeah, the first one is, again, awareness. The second one is our role as engineers to actually propose these things. The third one is to be able then to design them. But again, the good news is that we have the tools to do that. And then the fourth one is, as is in all the cases, is to be able to navigate politics and all these things that can certainly restrain things. I can tell you, for example, now in the United States, geothermal technologies are more feasible in some states as opposed to others. And in the US, gas is extremely cheap. And so unless there are tax credits and incentives there that people can use, these solutions are still too costly for the US. This is not the case, for example, in Europe. In Europe, it's very different. Like the cost per kilowatt hour, it's much higher compared to the US. So there are local and regional things that need to be addressed. And so clearly, tax credits and incentives can be key. And so I guess, again, as a community, it's our responsibility to manage and navigate the complexities associated with politics, with standards, with regulations, and so on and so forth, and try as a community to push things in the right direction, I guess.
Thank you. La pregunta anterior fue del Edgar Ángeles Moreno, gracias. Edgar Pérez Torres pregunta, ¿qué tipo de sensores son los que se utilizan para monitorear la temperatura de la ciudad?
Okay. There are a myriad of sensors available, I guess. So it's really, yeah, I don't know if it's the best moment. I can provide information via email, but I don't know if it's the best moment to advertise specific companies. But so the key, I guess, so there are many companies and many sensors available in the market. I guess the key aspect, in my opinion, is to select sensors that have appropriate accuracy, typically an accuracy of the order of 0.1, 0.2 degrees Celsius maximum. Like if more than that, we don't know really what we measure. But these sensors are available in the market, and their cost ranges from $20 to $100, maybe $150. So they are not tremendously costly. Of course, it depends on the numbers that we want, but they are there. Yeah.
Gracias. Francisco Armando Luna pregunta, yo tengo una duda respecto a la Ciudad de México, porque debajo de nosotros había un lago. ¿Ahí cómo afecta toda esta agua que aún se tiene al calentamiento debajo de la tierra?
Yeah. So, well, yeah, thank you again for the question. So, as we mentioned before, clearly, well, nowadays, Mexico City, I don't know data, so I am speculating over this, but the ground beneath Mexico City is warming up, for sure, has already warmed up. So if someone were to drill a hole in Mexico City and then outside of the city in a rural area, in a green area, there would certainly be a temperature anomaly, and this is due to the fact of the millions of buildings that you have built. So the ground is warming up. This heat could actually reach this underground water reservoir, very likely. Now, but I don't know. Again, I'm speculating, but I'm talking based on my relatively limited experience on this. So now, geothermal technologies could be used to, again, absorb this heat and bring it away. But I recognize that if not properly installed, geothermal technologies themselves could contribute to this warming or cooling of the ground. So now, this is why old standards prescribe temperature limits for the geothermal technologies to operate. So it's really what we typically do is that over 50 years or 100 years, we want to ensure that the temperature variations imposed by these geothermal technologies do not exceed certain limits. So again, these things, depending on the countries, are there. And if not available in a specific country, they can be taken as reference from other countries. And again, there are all the tools and the ways to actually avoid that they negatively contribute to the warming of underground water reservoirs or so on and so forth. So I guess the comment is excellent, is an excellent one, is an important one. My answer is, I believe that we have the knowledge and tools to control it and to to avoid unwanted impacts.
Gracias. José Luis González hace dos preguntas. La primera, ¿de qué manera se puede almacenar la generación de calor en el subsuelo o el proveniente de aire para usarlos posteriormente?
Well, so we can limit the amount of heat that diffuses underground in the simplest way by applying a thermal insulation on the intrados of structures. Now, the way through which we can actually absorb it and take it back is with these geothermal technologies. With energy geostructures, basically, once we thermally activate walls and the slab and piles, the structure themselves can absorb the heat and bring it up. So the idea is that there will be, as we have seen, there are pipes and there is water circulating the pipes. This water will exchange heat with the surroundings and will bring it away. Of course, these technologies will not allow us to absorb 100% of the heat that will be lost. So the efficiency is not going to be 100%, but they will be able to do something. Based on the results that we have obtained, the efficiency can be it typically ranges from 40 to 80, 85%, which means that basically we may miss only 15 to 20% into the ground. So they are a relatively efficient way to actually absorb back this heat. And then if we think about more traditional geothermal technologies like boreholes, we can drill geothermal boreholes next to buildings to absorb the remaining amount of heat. But again, the number one thing to do in order to limit subsurface urban heat islands is not necessary to deploy geothermal technologies. The number one thing to do would be to improve energy efficiency and thermally insulate underground building enclosure, have thermal insulation in building basements or in other underground structures. If we cannot do that, because oftentimes we cannot do that, then another idea can be to reuse that heat and capture it back.
Gracias. La siguiente pregunta es, para incentivar el uso de estas tecnologías, ¿hay certificaciones para incrementar el valor económico de determinada infraestructura?
Yeah, so these, for example, implementing energy structures can typically contribute to certifications like LEED, BREEAM, Energy Star. So since they are technologies that allow the harvesting of renewable energy sources, they typically contribute to going up in the grades and in the ranks of buildings. And so definitely, yes. So they can contribute to that. And I would even say it can be, they can increase the value of properties. So because properties that can say that 100% of their thermal energy needs come from renewable energy sources, I guess they are in a position to even sell apartments or whatever at a higher cost. And this is actually happening in a number of countries. So these are other benefits, yes.
Gracias. Siguiente pregunta, creo que ya es la última. Buenas tardes, me gustaría preguntar cómo la electroquímica puede contribuir positivamente al desarrollo de esta clase de estructuras. Pregunta Julián Estrada.
Okay. Well, so today I haven't talked about any electrochemistry at all, but so really the work that we're doing on electrochemistry is right now focused on using electricity to essentially for like ground improvement, and we're not studying the classical approach of electrokinetics, but rather a new approach that allows us to cement soils. So the idea is to use minimal amounts of electricity to for ground improvement, for cementation of soils, and so on and so forth. And the other things that we're doing related to electricity and electrochemistry are to essentially, we're studying new ways to store electricity into the ground or into structures. So I would say these are separate problems from those that I dealt with in the presentation today. But again, they are part of the research program that I lead at Northwestern, because we really study, we're interested in understanding how energy transfers influence the mechanics of geomaterials with a focus on heat flows and electrical current flows. And so, but today I only talked about heat flows. So I guess these electrochemical approaches are not relevant for mitigating subsurface heat islands or anything else. But I hope there will be other opportunities to talk about that. Yeah.
Thank you. Thank you very much, Alessandro. That was the last question. Thank you. Thank you so much for being today with us, sharing this very interesting conference. So I would like to share the certificate of the SMIG. You can see here. Okay. Thank you. Thank you very much. On behalf of the Mexican Society of Geotechnical Engineering, I present this certificate of recognition to Alessandro Rotaloria for his distinguished participation in this conference on the ground climate change, threats and resource for urban areas worldwide. Thank you. Thank you so much, Alessandro, for
Thank you
being.
for the opportunity again.
Would you like to talk some final comment?
No, I guess thank you for the opportunity. I hope it was interesting, and I'm happy to answer any other questions that may arise. So
Thank you. Thank you very much. I see you in the next conference, in the next Congress.
very soon.
Thank you.
Thank you again.
Gracias. Gracias a toda la comunidad mexicana de ingeniería geotécnica que estuvo presente en esta conferencia muy interesante. Y pues si tienen preguntas adicionales, pueden hacerlas llegar a través de la página del comité. Creo que el doctor Alessandro estaría gustoso de contestarlas, creo.
Sí, sí, sí.
Sí, muchísimas gracias a todos y pues bueno, nos vemos a la próxima. Gracias. Buena tarde.
Gracias. Buenas tardes.
Buena tarde.